Hello friends, welcome to this lecture on the course of computer-aided power system analysis. In the last lecture, we have introduced the basic concept of the state estimation technique, and in this lecture, we would be exploring more on this particular method. So, let us start. So, we are discussing state estimation technique. So, when we have started discussing about state estimation technique in the last lecture, we said that it is necessary for us to continuously monitor the system, let the power flow or the current magnitude over any line goes beyond their corresponding permissible limit. Now, we also said that if we know all the values required for performing the load flow analysis, then we could be simply keep on doing this load flow analysis periodically and then simply calculate the power flow as well as the current flow magnitude over all the lines and then take appropriate action whenever it is necessary. Then we also argued that sometimes or rather in many occasions it is not very convenient to get all these values of power injections which is required for the load flow analysis. Instead of this power injection values which are required for performing the load flow analysis, it would be sometimes much easier to get the measured values of the power flow over the existing lines, over some existing lines. Now, there is also another aspect of it. Another aspect is as follows. Again, we look at this power flow analysis. Again, our inputs are Vi, theta I for slack, Pi, Vi for PV and Pi, Qi for PQ. Now, in actual implementation, from where I will get this Pi, this Pi, this Pi and this Qi. We can always argue that this theta I would be always equal to 0. So, then therefore, we really do not have to measure it. These Vi's, this Vi, they are already known to us because we probably know that what is the setting of the voltage controller of the generator. So, then therefore, if we know that any particular generator is mandated to control its terminal voltage at let us say 1.01 per unit. So, then in that case we can say my Vi specified magnitude is let us say 1.01 per unit. So, then therefore, we can also argue that yes, probably for these two values we really do not need any meters, but then we need at least meters for Pi and Qi at the load buses because of this fact that in any system, the loads at any bus will keep on changing. So, then therefore, until and unless we know at each and every instant that what is the amount of load which is being consumed from any bus, right. So, we would not be able to know their appropriate exact values, and if we do not know their exact values, so then therefore, our load flow calculation itself would be erroneous, and if we get erroneous values of voltage magnitudes and angles at all the buses, we will get also erroneous values of calculated values of power flow over a line as well as the line current magnitude over a line. So, then therefore, we need to put meters here. Now, if I put a meter and even if I assume that I do have this communication backbone to transfer these measured values to some control center here. So, we say that this is control center. So, we do have some communication channel from here to here and from here to here to transfer these measured values to this control center. Now, there are two issues. First issue is that we are putting meters, and second issue is this communication channel. Now, what are these issues? So, two issues arise. One issue come due to the meters. Now, when you say that we are taking this measurement from the meters, we need to remember that no meter in this world is absolutely accurate. Each and every meter has got some inherent error. So, then therefore, if the actual accurate value is let us say 100 megawatt at some bus, and if this meter has got let us say 1% error, just 1% error. So, then this meter probably at some point of time it would be measuring 101 megawatt, or maybe at some other point of time it would be measuring 99 megawatt of power. So, then therefore, because of this error inherent in the meter, it will not ever measure this exact ideal values which is equal to 100 megawatt, rather it would be measuring some value which is not true value. So, then therefore, this control center, when it will get the measured values, this control center will actually get the values not exactly 100, but they will get 101 or 99. But even then we can argue, well, these errors are not very much, for all engineering purpose these values are acceptable. So, then therefore, even if we perform our load flow analysis with this small erroneous values, still we will get our the calculated values of real power flow as well as the line current magnitude within an acceptable error. So, then therefore, this calculated values of real power flow as well as the line current magnitude will give us an reasonable amount of confidence about the current health of the system, that is agreed. But now suppose this meter for any reason suddenly started malfunctioning. It can, because after all these meters are already put and it is not possible for anybody, and it is not possible for anybody to monitor this meter on a continuous basis. Now, suppose this meter has got somehow, due to some circuitry problem inside it, has started malfunctioning. So, then therefore, now this error, instead of becoming 1%, now this error let us say becomes suddenly it is now operating with a 10% error. So, then therefore, if this actual value is 100 and instead of sending 100, it is now sending either 90 or maybe 110. These values are unacceptably large, these values contain unacceptable level of error. So, if we calculate the load flow analysis with these erroneous values, so obviously we are going to get a very erroneous estimate of the system. So, then therefore, when you are talking about the issues meters, this issue is essentially errors in meter, errors in meters. So, this is the basic issue. Now, what is the issue regarding this communication channel? This communication channel, we are assuming that this communication channel has got no error as such now. So, then therefore, if the value sent by the meter let us say 100, so this communication channel also is sending a value of 100. But it may sometime happen that due to some error in the communication channel, of course, nowadays with the advancement of the communication technologies, this chance of this error is pretty small, but even then it may happen that sometimes this communication channel fails. So, then therefore, instead of getting these values 100, we may get some completely garbage values, or sometimes we even may not get any value. So, then therefore, communication channel also has got some error. So, then therefore, whenever we are trying to measure any values, let us say injected power values by using meters, these values which are ultimately being transmitted to the control center may contain very large amount of error. Now, the question is, of course, this very natural question is, in the last lecture we said that, well, instead of again we are taking this 3 bus system. So, this is the slack bus, and we said that we are measuring here P12, this is bus 1, this is bus 2 and this is bus 3, P12, Q12 and let us say I12 magnitude, and let us say here we are measuring P23, let us say. So, I have got 4 unknowns, so I will get 4 equations, so I can solve. Now, the question is, again the same question come. Now, here suppose my control center is here, some control center is somewhat here. Now, here also we have put 3 meters, 1, 2, 3 and also we have put another meter here. So, then here also we have put 4 meters. Now, because we have put 4 meters, now here also because we have put meters here, so this meter also can have error, and although these meters are located at our control center, again it is not possible for anybody to continuously monitor this meter whether they have started malfunctioning or not. So, then therefore, this meter also may contain error, again this meter also may contain error. Now, again because we have said that this is 200 kilometers, so again from here to here also we have to transfer this value from this location to this location. So, this is a communication channel and this communication channel also may contain error. And although these meters are located at the local station itself, but even then there has to be some communication media, some links, something which will also transfer these values to here, from here to here, and this here to here, and similarly from here to here. So, there also can be some error. So, then therefore, what we can see is that whether I do power flow analysis, that I mean whenever we are taking some measurement either for the purpose of doing power flow analysis, or we are taking some other measurement to eliminate some of the difficulties associated with measuring the injected quantities at different buses, but inevitably these measured quantities will be associated with 2 types of error. One error is due to the meter error and another error is due to the communication error. So, now, so then therefore, the question comes, now in the case of power flow analysis, whenever we have done our power flow analysis, what we have assumed? We have assumed that whatever input values are available to us, these are the input values. So, whatever input values are available to us, these values are ideal, absolutely accurate without containing any error. But now, our problem becomes a little more difficult and complicated, because in the case of when we have done power flow analysis, we have not considered the possibility of any error in any of the measurements, because we have just now argued it is almost always true that to get these values of this pi and this qi, you have to put some meters. So, now our problem becomes more complicated in a sense. Now, we have to consider the possibility of errors in our measured quantities. So, whether we are utilizing measured quantities for the purpose of power flow analysis or for any other purpose. So, then we have to consider the possibility that we have got some associated error in the measured quantity, and we have to now because there are now errors in the metered quantities, errors in the measured quantities. So, then therefore, we would not be really able to calculate the ideal values of our unknown quantities. We have to only estimate, we can only estimate their values, that is. So, then therefore, the state estimation technique is basically concerns about estimating the unknown quantities in the presence of measurement error, or when we say that when we use the term measurement error, we are actually taking into account the fact that this error may come due to the inherent error of the meters, or may crop up due to the error in the communication channel, or both. So, now our problem is that how to calculate or estimate the unknown quantities in my system in the presence of metering errors. So, that is the essence of the state estimation method. So, then the essence of state estimation method is estimating the values of unknown quantities in the presence of metering errors. We are saying that we are trying to estimate the unknown quantities because of this fact that because I have got input quantities which are metered quantities, which are measured quantities, I have got inherent error. So, then therefore, my measured quantities which are nothing but the input to my algorithm are not accurate, are not ideal. So, then therefore, my output of the algorithm, whatever that is, that be, so then therefore, my calculated quantities will also not be ideal, right. So, then therefore, our effort or our goal is now to calculate these values, or rather they estimate these values such that the effect of these measured errors are minimum. So, the whole process of state estimation, we call it state estimation, SE, state estimation, call is SE. So, the whole purpose of SE is to estimate the values of unknown quantities such that the effect of the errors are minimized. So, the goal is to estimate. Again I repeat, we are using the term estimate, not calculation, because or to solve, because when we say solve, we assume that my input quantities are absolutely ideal, and my, so then therefore, my output quantities will also have their most accurate values, or rather the ideal values. But here, because our input quantities are having errors, so then therefore, my output quantities will also have errors. So, then therefore, I never can calculate their ideal values. So, I can only estimate their values such that the effect of error is minimized. So, estimate the values of the unknown quantities such that the effect of measurement errors is minimized. So, that is the basic goal of state estimation technique. Now, the most popular method for estimate the values of the unknown quantities such that the effect of the measurement errors is minimized is called weighted least square method. Weighted least square, so we call say WLS method. So, we are now going to discuss about weighted least square method. Now, here we need to remind ourselves that our goal is to do state estimation of an electric power grid. That is our final goal, which we will do, but to introduce the basic theory and the concepts of weighted least square estimation method, we will first take a very simple circuit, a DC circuit. So, let us take a DC circuit, something like this. I am just drawing an arbitrary circuit, honestly, nothing much, something like this. So, there is a current source, there is a voltage source. So, this is V, this is R1, this is R2, this is R3, this is R4, this is R5, this is R6, this is V and this is I. So, this is a voltage source, this is a current source. Now, suppose let the unknowns are V and I. So, I do not know what is the value of this V and I do not know what is the value of I want to calculate their value. So, now for that what I do, let us say I am simply taking the I am taking some measurements. So, I put some ammeter here, say I put some ammeter here, So, I measured these values I1, and let us say I put one voltmeter across this, let us say. So, this value is voltage, and let us say I put another voltmeter across it, let us say this is V2. Let us say I do put another voltmeter across it. I am just taking arbitrarily. Let us say I am also putting another voltmeter across it, let us say V3, and so on and so forth. So, I have put 4 meters, and then I am taking this measurement. So, I have put 4 meters. So, I know this measured values, and from this I would like to estimate the values of V and I. Now, from our basic circuit analysis, because after all this is a simple linear circuit, all these are resistance and this is voltage source, this is current source or whatever it is, or and then what we can do that now if I do this analysis. So, then what I will find is that if I write the expression of I1 would be some constant, let us say A1 into V plus some other constant into A2 into I, and where A1 and A2 are constants, some constant, and these are actually all functions of all Ri, where for I is equal to 1 to 6. So, then therefore, this A1 and so then A1 would be some expression involving R1, R2, R3, R4, R5, R6. Similarly, A2 also would be some expression involving R1, R2, R3, R4, R5, R6, right. I mean, if we do just our simple circuit analysis as we do in our first year, so we will be find out this expression. So, similarly what I write is, so let us say that I1 let us say A1 let us say V and let us say A2 I. Similarly, let us say V1 would be something A3 into V plus A4 into I. Similarly, V2 would be let us say A5 into V plus A6 into I. Similarly, V3 would be A7 into V plus A8 into I. So, here we again note that all AI I is equal to 1 to 8 are all constants and functions of R1, R2 to R6, right. Now, what we have done, we have actually taken 4 measurements. So, let us say this is M1, we call it M1. So, this is measurement 1. So, this is measurement 2, this is measurement 3, this is measurement 4, and my unknowns are, we are saying that is V and I. So, for our analysis we say that my unknowns I always denote as state variables x1 and x2. So, here x1 and x2. So, then therefore, I can say so now if I now rewrite these equations in the common parlance. So, what I will write is that M1 is equal to H11 x1 plus H12 x2, where of course, I am writing A1 is equal to H11, A2 is equal to H12. Similarly, M2 is equal to, I can write H21 x1 plus H22 x2. Obviously, A3 is equal to H21 and A4 is equal to H22. Similarly, I can write down M3 is equal to H31 x1 plus H32 x2, M4 is equal to H41 x1 plus H42 x2. of course H31, H32, H41, H42 we can identify. I mean let us just write it for the sake of completion. A5 is H31, we are just denoting it for the purpose of um, more of a general analysis. So, A6 is equal to H32 and A7 is denoted as H41 and A8 is H42. Now, what happens? These values M1, M2, M3, M4, these are the measured values. Now, these quantities H11 x1 plus H12 x2 is the ideal values, that if this value is, let us say, I mean if this value, let us say if V is, let us say 10 volt and if let us say I is equal to 5 ampere. So, I know what is A1 and I know what is H11, I know what is H12. So, if this value is, let us say, so now if I put x1 is equal to 10, so this is 10 is equal to x1, this is 10 is 5 is equal to x2. So, now if I put 10 is equal to x1 and 5 is equal to x2 and h11, h12 everything is known. So, then this expression will give me the ideal value, this is the ideal value. But what this ammeter will measure, because of this inherent error, this meter M1 or this ammeter will measure this ideal value plus or minus some error. So, this meter, because of its error, it will not report this ideal value, this meter will actually report some error along with this ideal value. So, then therefore, if this ideal value is, let us say, for example, let us say H11 is, let us say 5 and let us say H12 is, let us say 2. So, then when here the ideal value of M1 is, M1 would be H11 into x1, that is 50 plus 2 into 5, that is 10, that is 60. So, ideal value of M1 is 60, but this is an ammeter. So, then this has got its inherent error. Now, the point is, now we also need to remind ourselves one very basic fact of that if I take the measurement of the same quantity in a circuit by the same error repeatedly, then the value what we get from that meter is not the same every time. That means, what I am trying to say is that suppose I have a very simple circuit, this we already this kind of experiment you always do. Suppose I have put an ammeter here, this is an ammeter and this is an resistance and this is a very simple circuit, there is nothing in it V R. So, I have put a resistor, so let us say this is 100 volt and let us say this is 10 volt, so 10 ohm, and if I put an ammeter here, so then if I now measure this current repeatedly by this ammeter, I will not always get 10, I will get probably sometimes 10.1, probably 9.92, sometimes maybe 10.05, sometimes maybe 9.938, whatever it is, but probably never I will get exactly 10. And why these are getting these values instead of 10? See, this is the ideal value, but we are never getting ideal value, we are getting some erroneous value. That erroneous value we are getting because of this inherent error of this meter, and this inherent error is actually random in nature. So, if I say that this error is, let us say, if I say that this meter has got an total error is, let us say, plus minus 1%, that does not mean that this meter will always give plus 1% or minus 1% error. This, when I say that it is a plus minus 1%, this is actually the maximum value, but in practice whenever it will measure some quantity, it will give some error which is random in nature within this plus minus 1 range. So, then therefore, what is happening is that this measured value will have some, so then ideal value plus some error here. So, and these errors are actually random in nature. So, then therefore, our lab experiments, when we do take some measurement by utilizing some measure, we usually what we do, we take the repeated measurement of the same quantity and then we take the average. Why do we take the average? Because these errors are basically random in nature. So, then therefore, sometimes these errors are positive and sometimes these errors are negative. So, then therefore, if I take their average of some repeated measurement, these errors will cancel out each other. So, then therefore, this average value would be closer to this ideal value. But the point to be noted here is that this any meter m will give the ideal value, we will say x true plus some error, and this error is in random in nature. So, then therefore, here in this case we can say now basically this is the true value, but unfortunately I do not know what is this value, but what this meter will give, that this quantity plus some error E1. Similarly, M2 will also give some error E2, M3 will also give some error E3, M4 will also give some error E4. So, this is the measurement model. So, what we have got? We have got now essentially for this case, we are taking a very simple case to develop the theory. So, what we have got? We have got a very simple circuit and we are got two unknown quantities which we call them as x1 and x2. To estimate these unknown quantities, we are utilizing 4 meters and we are now writing down the expression of the measured quantities measured by these 4 meters. So, when we write the expression, we are actually writing the expression of the ideal quantity, ideal value which these meters will record if everything had been ideal. But in actual life, we note that these meters will actually give us a measured value which is equal to the ideal value plus or minus some error, plus or error. Now, here when I say E1, E2, E3, E4, this E1, E2, E3, E4 they can take either positive value or negative value which we do not know, these are all random in nature. So, then therefore, the measured value M1 would be this true value plus error, measured value M2 would be true value plus error, measured value of by M3 is the true value plus error, measured value of M4 would be true value plus error. So, now our task is to estimate x1 and x2 from these measured quantities M1, M2, M3, M4 such that the effect of these random errors E1, E2, E3, E4 would be minimized. So, this will continue from the next lecture. Thank you.